Okay, we talked a little bit about inverse functions last year. You may recall when we were looking at functions right at the start of the year. So a reminder of what inverse functions are. To start off with, in order to have an inverse function, the original equation, the original curve, has to be a function itself. Now remember, for it to be a function, then for every x value in the domain, there must be a maximum of one y value. Visually, we used a vertical line test. We can slide that along and make sure it only cuts at a maximum of one time. Now, if we swap the x and the y's around, so y equals x squared becomes x equals y squared, y equals x cubed becomes x equals y cubed, and so on, then that relation is called the inverse relation. So there's an example there, y equals x cubed plus x, swap them around, x equals y cubed plus y. But now, if this new inverse relation also satisfies the condition for a function, then it becomes an inverse function. Okay? So visually, we used a horizontal line test on the original function, because when we swap the x and the y's become the x's become the y's. So the vertical line test for the function, horizontal line test for the inverse function. The symbol we use is kind of unfortunate. It looks like we're saying to the power of -1, but it's not. It just means inverse function. Inverse function. All right. If you were to look at both of them together on the same number plane, then they would be reflections of each other in the line y equals x. So y equals x acts like the symmetry. So if AB is a point on the original function, BA will be a point on the inverse function. The x and the y's swap around. The domain of the original function will become the range of the inverse function. So the original function has a domain of, x is in between 2 and -2. Then the range of the inverse function would be y is in between 2 and -2. And the same thing happens with the range. The range of the original becomes the domain of the inverse. So as I say, testing, the easiest way is to do it visually with the horizontal line test. So let's have a look at our basic parabola there. There's y equals x squared. Now, there's a horizontal line, cuts it twice, no good, no good. So nope, it has an inverse relation, but it doesn't have an inverse function. The cubic, y equals x cubed, doesn't matter where I draw a horizontal line, it'll only cut it once. So yes, that one will have an inverse function. Now, the other way we can do it is via algebra. We can swap the y's and the x's round and then make y the subject. If we come up with something that is unique, then it's an inverse function. So back to our parabola, swap the x and the y's around. But when I make y the subject here, I'm going to go y equals plus or minus. So it's not unique. There's two possibilities. So not unique, so again, doesn't have an inverse function. Whereas the cubic, swap the x and the y's around, we get x equals y cubed. Make y the subject, we get y is the cube root of x. And remember, we're dealing with just real numbers here. There is only one cube root of x in the real number world. And so that is unique. And so yes, that one is an inverse function. Now what happens? Got a lovely little test which, well, we probably don't use that often. But basically inverses and functions should cancel each other out, like everything else in maths. You know, multiplication, division cancels out, addition, subtraction. So if I was to sub the original function into the inverse, it should cancel out and I'm left with x. And the other way around should work as well. If I substitute the inverse into the original function, I should just be left with x. So for a bit of fun, let's have a look at this one. 2x plus 1 on 3 minus 2x. Let's find its inverse. This is a function, by the way, because remember I could do a polynomial division. Turns out to be a basic hyperbola. It's been shifted. That becomes, well, swap the x and the y's around, a little bit of algebra, and then we end up with y equals 3x minus 1 on 2x plus 2 would be the inverse function. So if I substitute the original function, 2x plus 1 on 3 minus 2x, into the inverse, so everywhere I see x, replacing it with the 2x plus 1 on 3 minus 2x, this should equal x. Fractions on fractions, multiply everything by 3 minus 2x, tidy up, yep, we end up with x. As I say, the reverse should be true as well. So if I substitute the inverse function into the original, so this time everywhere I see x in the original, replacing with 3x minus 1 on 2x plus 2, this also should be able to be manipulated, and again, we come down to x. Okay. Restricting the domain, because when you think about it, most curves will fail a horizontal line test. Because most curves will have a turning point at somewhere, and as soon as you've got a turning point, horizontal line test, no good. So in order to create an inverse, we restrict the domain on the original function. And we just want a piece of the original function that will only cut it once to satisfy the horizontal line test, but capture hopefully all of the range, but as much as possible. So y equals x cubed, of course, I don't need to restrict it because we already decided it has an inverse. Let's just have a look at y equals x cubed. There it is. Its domain is all real x. Its range is all real y. Inverse function, swap the x and the y around, we get y is the cube root, or x to the power of a third. Watch what happens. The domain and range swap around. I know it looks like it's the same, but trust me, they've swapped. The original domain was all real x, so now the new range is all real y, and the original range was all real y, so now the domain is all real, possibly not the greatest example I could have picked. All right, if we were to draw it, there we go. The red one would be the inverse. I don't know if you can see my green dotted line there. There's y equals x. Basically reflecting the blue curve in the green line. If I had to draw that, which obviously I did because there it is, the important points to plot, any point of intersection with y equals x, of course, because we know they're going to stay the same. Turning points, well, this one doesn't actually have any turning points, but perhaps this sort of peak on the curve here, reflect that across. As many points as you need, I guess, until you get a feel for what the curve is doing. But on that note, if I had to find those point of intersection between y equals x cubed and y equals x to the power of a third, I would not solve x cubed and x to the power of a third simultaneously. I would solve x and x cubed simultaneously, because that's going to be an easier equation to solve. So if you want to find where a function and its inverse meets, you don't actually have to say one function equals the other. Just make one function equal to x, because you know they're going to meet on the line y equals x. And that will usually be an easier equation to solve. All right, let's have a look at our exponential. There's our basic exponential, e to the power of x. We know it goes through at 1. It has a domain of all real x. It has a range of y is greater than 0. So my new function, swap the x and the y's. We get x equals e to the y. I want to make y the subject. To undo the exponential, we log both sides. So y becomes the natural log of x. Its domain will become x is greater than 0. Its range will become all real y. Now, let's reflect that in y equals x. There it is. And in fact, they don't have a point of intersection in that case. The log curve and e to the x never meet. One where we're going to have to restrict the domain. Y equals x squared. There's the parabola. Fails the horizontal line test. Damn. All right, its domain at the moment is all real x. Its range is y is greater than or equal to 0. But, damn, no inverse. So I want to just get a piece of that parabola to get as much of the range as possible. I could cut it two ways here, depending. I mean, I could use the right-hand side of the parabola. I could use the left-hand side of the parabola. I suppose the sorts of things we want to try and do. We want to include 0, if that's part of the range. Well, in this case, it doesn't matter which half I go. We tend to go with the positives rather than the negatives. So I'm going to use the right-hand side of the parabola. Now, it's not wrong to go to the left-hand side. So my restricted domain is x is greater than or equal to 0. That does not change the range. If I only use points greater than or equal to 0, I still get that complete range. So what does the inverse function, because now it will be an inverse function, become? Well, it's y equals x to the power of a half, or the positive square root. If you were to, and we'll draw it in a sec, let's get our new domain is greater than or equal to 0, our new range, there it is. And when we reflect it, there it is. It's the top half of the parabola. Had I chosen the other branch, then I would have got the minus the square root of x. I would have got the bottom half of the parabola. A few years ago, they gave us e to the minus x squared. Clearly, that one does not satisfy the horizontal line test. Well, they tell us it has 2 points of inflection. We can see that quite clearly. It does change concavity, and it's symmetric. Find the x coordinates of these points. Right. In this case, I don't actually have to test. I still need to solve the second derivative is equal to 0, because we've got to find those points of inflection, and we know the possible ones occur when the second derivative is equal to 0. And when I solve that, so the first derivative will be minus 2x e to the minus x squared. Second derivative, got to use my product rule, then collecting terms. There it is, 4x squared minus 2 e to the minus x squared. If we make that equal to 0, I only get two solutions. Now, because they've told me it has 2 points of inflection, and I've come up with only two possibilities, I don't need to test them. Okay? Had I come up with 3, then yeah, okay, I've got to test them to find out which 2 of the 3 are the actual inflection points. So we don't need to waste time here and actually test them. So it's plus or minus 1 on root 2. Don't have to find the y values because the question has only asked for the x coordinates. Part B, explain why the domain must be restricted. Basically, this is talking about the horizontal line test. So you could use those sort of words. What did I do? I actually went to a very formal definition. Look at that, 1 to 1. How fancy. In order to have an inverse function, there must exist a 1-to-1 relationship between the domain and range. In other words, every value in the domain gives a unique value in the range. That's a really fancy way of saying there's a maximum of one y value for every x value. So that explains it. I suppose they probably would have accepted fails the horizontal line. It would have been worth 1 mark. I mean, yeah. All right, let's go and find the formula. We're going to restrict it to x is greater than or equal to 0. So we swap the x and the y's around. We now want to make y the subject. I get down eventually where we got minus y squared log x, y squared minus log x. I brought the minus inside the log to make it the log of 1 on x, or x to the negative 1. So we get plus or minus. There's our two possibilities. Which one of those two possibilities do I want? Well, we've restricted the domain of the original function to be x is greater than or equal to 0. Therefore, the range of our new one has to be positive. So I've got to pick the positive square root. Right. So y is equal to the square root of the log of 1 on x. State the domain of our new inverse function. Well, the domain of the inverse will be the range of the original one. And if we have a look at our graph, it was x is in between 0 and 1, but not including 0, went asymptotic. So that would become the domain of the new function. And of course, to finish it off, go and sketch it. Ta-da! You like it? That's what it looks like. All right.